Hi Bobcats. In this video we're going to explore the last of the connections that we're going to make between the equilibrium constant and delta G. Our main objective for this one is to find a mathematical relationship between delta G naught and the equilibrium constant K. So here's what we're going to do to see the relationship between K and delta G. We already have this relationship that says delta G is equal to delta G naught plus RT natural log of Q. But if we are at equilibrium, Q is equal to K, so we can make that substitution. In place of Q, we can put K. And then when we're at equilibrium, delta G goes to 0. There's no drive to go in either the forward or the reverse direction. So here we go. We've got 0 is equal to delta G naught plus RT natural log of K. If I rearrange this a little bit, get these guys on opposite sides of the equation, that's going to throw a negative sign in there, and we have delta G naught is equal to minus RT natural log of K. Well, this is great if we have K and we need to find delta G naught, but if we need to go the other way, if we have delta G naught and we want a value for K, we've got to do a little bit of algebra. And we end up with an expression that says K is equal to E to the minus delta G naught over RT. Remember, this is E as in the opposite function of natural log. E is a constant, 2.7 something. Another way of writing that is EXP of negative delta G naught over RT. Those two equations are real important for connecting delta G naught and K. So I want to think just a little bit about what the meaning of some of this. If delta G naught is negative, we know that that means it's a spontaneous reaction. That means it's going to want to go in the forward direction. And so if delta G naught is negative, that means that K has to be bigger than 1. And so if K is bigger than 1, that means that the equilibrium position favors products, right? And so these two things are saying sort of the same thing, that if our K is bigger than 1, the equilibrium favors products, and the reaction is going to go in the forward direction. But if delta G is positive, since this equation has a negative sign in it, that means that the natural log of K has to be negative. So we have a negative times a negative makes it positive. So if the natural log of K is negative, that means that K has to be less than 1. And so that means that the equilibrium is going to favor reactants, and the reaction is going to be spontaneous in the reverse direction. So we are asked in this problem to find the standard Gibbs free energy change in kilojoules per mole, and we're given K for, it's actually Ka for nitrous acid. So the equation that we are going to use to connect these two is that delta G naught is equal to minus RT times the natural log of K. Let's think for just a moment about what value we want to plug in for R here. In terms of joules, R is 8.314 joules per Kelvin. And we were asked to report our answer in kilojoules. So I'm just going to go ahead and move the decimal 3 times, which will put 2 zeros out there in front. So we'll have a negative 0.008314 joules per mole Kelvin. I think I got a little sloppy there. I left off my moles on the original value up there for R. And then for T, it's 298 Kelvin. And then we'll have the natural log of K, and I've totally run out of room here. Inside of those parentheses, we should have 4.0 times 10 to the negative 4. All right, let's go ahead and run this through the calculator. Again, I use a scientific calculator, not a graphing one. So for me, it's easiest to start with the natural log part. So I'll do 4EE 4 negative. So that's 4 times 10 to the minus 4. Now I'm going to take the natural log of that number. and I'm going to multiply that times 298, and I'm going to multiply that times R 0.008314, and there's a negative sign on that, so I'll change the sign. And in the end, I get a delta G naught of 19.4 kilojoules per mole. And I just realized I blew it again on my units right there when I plugged in that value for R. That should have been in kilojoules. All right, so that gives us a delta G naught of 19.4 kilojoules for this dissociation reaction. In this example, we're going to go the opposite direction. We have delta G naught. We calculated that in an earlier problem, and for this reaction we found delta G naught was 173.1 kilojoules. Now we need to see what the value of the equilibrium constant is for this reaction. Notice that delta G is positive. That would mean that the reaction is non-spontaneous, so we would expect for this to lie much closer to the reactants than to the product, so we should be getting a pretty small equilibrium constant for this. Our equation for the equilibrium constant was that it is e to the negative delta G divided by RT. I think I'd like to do some pre-calculation here. We already have a value for our delta G naught, so I'm going to go ahead and calculate negative delta G naught over RT ahead of time. So negative delta G naught over RT, and we need to make sure our units are compatible. I'm just going to go ahead and do everything in terms of joules instead of kilojoules. So up in the numerator for the negative delta G naught, I'm going to plug in a negative 173,100 joules. Right, that is taking the value that we were given in kilojoules, moving the decimal 3 times to get joules. Then down in the denominator for R, I'll plug in 8.314 joules per Kelvin, and the temperature is going to be 298 Kelvin. So the kelvins cancel out, the joules cancel out, and we'll be left with a unitless number. So I've got 173,100 divided by 8.314 and divided by 298. And that gives me a value here, including that negative sign, of negative 69.87. So to find our value for K, it'll be e to the negative 69.87. Make sure you know how to use this button correctly on your calculator. On my calculator, it's the second function under the natural log. And so I hit second function and e to the x. And the value that I get is 4.54 times 10 to the negative 31. So that's a real small equilibrium constant. This reaction greatly favors the reactants over the products. On this slide, we're asked to interpret the values for Q, K, delta G, and delta G naught. We're told that a reaction is spontaneous under standard conditions. So that first phrase there, being spontaneous under standard conditions, means that delta G naught is negative. And so how could we change the concentrations to make it non-spontaneous? All right, so our delta G naught has a negative value, and so that would make tend to make delta G a negative number, but we can mess around here with the concentrations and change Q. We just need to make Q a large positive number so that the natural log of Q is a large positive number, and the second term, RT natural log of Q, becomes bigger than delta G in size. And so we're adding a large positive number to our negative delta G and change delta G naught and changing overall delta G to be a positive number. So that means that we need, or we want, Q to be a very large positive number. And remember, Q generally has the form of products over reactants. And so that means for Q to be a large positive number, we would want to have a whole lot of products and only a little bit of reactants. And that scenario, where we have lots of product and very little reactant, will make this particular reaction non-spontaneous. For this chapter, we had a lot of learning goals. We picked up the second law and the third law of thermodynamics. Let's see, there's the third law. We added that to the first law, which we picked up in Gen Chem 1. In addition now to delta H's, we've got delta S's and delta G's. Delta H's give us information about is it endothermic or exothermic. Delta S's give us information about our products more disordered or less disordered than our reactants, and delta G gives us information about spontaneity. We also took a brief look at standard conditions versus non-standard conditions, and we saw the relationship between delta G naught and the equilibrium constant. So lots of stuff going on in this chapter.